So we started with a complex representation of bandpass signals and systems.
Okay, very good. Very good. Thanks. Uh, yeah, to add to that, actually what I did in that, the complex representation of bandpass signals and systems. Now, hope I might have taken two equations, right? With respect to the representation of a bandpass signal in terms of its complex envelope. Then I said, what is the difficulty or complexity involved with those two equations? Isn't it? Yes, sir, people are getting my point. I said, how do we represent? Just let me present. Yeah. So I started with the representation of a bandpass signal in terms of its complex envelope, right? That is the first equation. I said S of t is equal to real part of S tide of t into e power j 2 pi f c t. And in the same way, I said, how do we represent the bandpass system, right, in terms of its complex impulse response? That is, h of t is equal to real part of S tide of t into e power j 2 pi f c t, right? I said in these two equations, we are finding the presence of the exponential factor, right? And this exponential factor complicates the analysis of the bandpass system, right, which is driven by the bandpass signal. Okay. Hope you are getting my point. I have a bandpass system having an impulse response h of t, right? For that, the input is what? The bandpass signal. But looking at the expression of these two equations, what I said, these two equations are multiplied by the exponential factor, which will complicate the analysis of the bandpass system. Okay, that bandpass system is driven by this bandpass signal. Then, how do we simplify this? How do we overcome that complexity? So that is a question, right? So the analysis of this bandpass system can be simplified through the combined use of this complex low pass equivalent representation of the bandpass signal, okay, and with the complex low pass representation of the bandpass system, right? So which is characterized by its impulse response. Okay, so already we have discussed how do we represent that. So here there is a procedure, okay, for doing that. So actually there are two ways to do that. One is the time domain procedure, and the second one is the frequency domain procedure. Okay, first let me discuss the time domain procedure. Okay, so how do we go about this? Hope you are getting my point, what I said. Yes, my dear students, are you getting what I am saying?
Sir, can you repeat how to overcome it, sir?
I have not yet discussed about how do we overcome that complexity. Okay, I'm supposed to discuss that. So as what I'm saying is the bandpass signal and bandpass system. Okay, in both the equations, the exponential factor is there, right? So the analysis of the bandpass system driven by this bandpass signal becomes complex or complicated with the presence of this exponential factor. Okay, to simplify that, to simplify the analysis of the bandpass system, which is driven by this bandpass signal, okay, I said we can represent or we can use the complex low pass equivalent representation of bandpass signal, and as well as the complex low pass representation of the impulse response of the bandpass system. Okay, so by the combined use of those two, we'll be able to simplify the analysis of bandpass system driven by the bandpass signal. So to understand that procedure, I said there are two ways. One is the time domain procedure, and second one is the frequency domain procedure. So first, let me take up the time domain procedure. Okay. So maybe at the end of this lecture, we will be able to understand how could this either time domain or frequency domain procedure as simplified the analysis of the bandpass system, which is driven by the bandpass signal. Hope I am clear.
Yes, sir.
Yeah, thank you. So let me take up first the bandpass, that is a time domain procedure. Sorry. So first make this bigger. One minute, I will. Yeah. Yeah. So I said there are two procedures. No, first one is the time domain procedure. So let me start with time domain procedure. Okay. So let me consider the signal x of t. Okay. So where x of t is the output signal of the bandpass system. Means if I consider a system, so this is my bandpass system. Okay, the input signal to this bandpass system is what S of t. Okay, so S of t is basically a bandpass signal, right? It is basically a bandpass signal. So if I write just PP signal, hope you understand, all of you. It is a bandpass signal, and the output of this bandpass system, I am representing it by another variable called x of t. Okay, so this x of t is also a bandpass signal. Is also a bandpass signal. Okay. So now let me represent this bandpass signal x of t, that is output of the bandpass system, in terms of its complex envelope. Okay. So similar to S of t, any one of you can say how can I represent x of t in terms of its complex envelope? Yes, I am asking you people to just cope up with me so that I can proceed further. I said x of t is a bandpass signal which I am applying it to the bandpass system. Okay, this bandpass system is having an impulse response h of t. So of course, which I have not specified here. Let us assume that is h of t. Okay. Then output of this bandpass system is another bandpass signal. So which I am representing it by x of t. Now I have asked you people to say how do I represent this x of t in terms of its complex envelope. So similar to s of t, you can tell how can we write x of t in terms of its complex envelope.
Real part
Just
of
now, yeah, x of t, right? X of t. Just 1 minute. Yeah. So x of t will be equal to a real part of
x side of t into e power j 2 pi f c t.
x tied of t into e power j 2 pi fct, right? The same way what I have expressed on the top, I am just asking you people to say in terms of x of t, for x of t. Okay. So let me call this as equation 3. Equation 3. Okay. So I said x of t is the output signal, right? And I can relate this x of t and as well as s of t, right? How do I relate that? If I take h of t as the impulse response of this bandpass system, right? H of t as the impulse response of this bandpass system. Then how do I relate x of t in terms of s of t? If anyone can say, how do I relate x of t in terms of s of t? How output of the bandpass system is related to the input signal s of t? I'm asking. Right, this bandpass system is an LTI system, right? Linear time invariant system, having an impulse response h of t. So how do we write the output of this bandpass system?
So convolution of input signal and its impulse response.
Very good, very good. So that is the response, what I am expecting, okay? So I can write x of t is the output of the bandpass system, which is equal to what? As you said, s of t, that is the input signal, convolved with the impulse response of the bandpass system, h of t. Okay. So next, other people should also communicate because only I am finding Skanda and Ramesh responding today. Yes, others. So now I wrote how do I relate the output signal of a bandpass system with the input signal, right? So convolution of the input signal with the impulse response I write. How can I write this in convolution integral form? Convolutional integral form. Yes, quickly, other students should say convolutional integral form. Convolution integral.
Integral
What?
minus infinity to infinity.
Okay.
S of tau
Huh.
into h of t minus tau d tau.
Very good, very good. Right? So that is the convolution integral. Yes or no? Yeah. So I can write integral from minus infinity to plus infinity. Okay. Either I can write s of tau into h of t minus tau into d tau, or h of tau into s of t minus tau into d tau also, right? Any one can be shifted, either the signal or the impulse response. Is that fine? You all agree with me?
Yes, sir.
Yeah. Yes, this understanding is there, then I can go ahead. So h of tau into s of t minus tau into d tau. Just I expressed the above equation in terms of its convolution integral. So let me call this as equation 4. So what you will understand, if you know the basics, then you will be able to go every step, right, without any finding difficulty, right? Okay. So just it is a basic, just I expressed output of the bandpass system in terms of its complex envelope, and then I related the output of a bandpass system with the input signal, then I wrote the convolution integral. Okay. Now, let me express the impulse response of the bandpass system in terms of its pre-envelope. Okay. Yeah, for this also, I think people can say already you all know what is pre-envelope. How do I write, okay, the pre-envelope of the impulse response of the bandpass system? Yeah, quickly, before I call your names, I think on your own, in terms of, yeah, in terms of pre-envelope, in terms of, yes, Naurin saying something.
So I was telling the equation for it.
Yeah, please tell, I could not hear. In terms of pre-envelopes, we can, yeah.
So for impulse response, right?
Yeah, for impulse response, how do I express in terms of pre-envelope? That is h of t is equal to, what I can
H
write? H
um,
plus of t,
H,
right? Yeah,
H plus
very good. So
T
the real, yeah, the real part of h plus of t, can I write like this? H plus of t, we know how do we write, right? H of t plus j into h hat of t, if I am correct. So real part of that will be h of t. Hope understood? Because, so let me write here, because I can define the pre-envelope of the given signal, right? H plus of t is equal to h of t, right, plus j into h hat of t. You all agree with me this? Because in the previous case, I might have taken s of t, right? S of t is equal to, that is s plus of t is equal to s of t plus j into s hat of t I used to write, right? Here for impulse response, I am writing like this. Is it fine? Yes, I am asking, is it fine?
Yes,
sir.
sir.
Yeah, thank you. In the same way, okay, for signal s of t also I can write, right? And so s of t is equal to, s of t is equal to, I can write real part of s plus of t, real part of s plus of t. Okay, so because I know s plus of t will be equal to what? S of t plus j into S cap of t. Okay. Yeah. Now just let me substitute in place of h of tau. Okay. This value in terms of pre-envelope. Let me express the equation 4. Let me express the equation 4 in terms of its pre-envelope. Hope noted now. I think if I move up is fine. So now let me write x of t in terms of its pre-envelope. So therefore I can write x of t will be equal to, so integral from minus into infinity. Okay, so real part of h plus of tau into real part of what I can write s plus of t minus tau. Okay, t minus tau into d tau. Yes, any questions so far? Let me call this as equation 5.
Sir, can you scroll a bit up, sir?
Yeah, that is why I asked you now. See, you should also understand my difficulty. Scrolling up, scrolling down. I think people should write immediately what I write. Is that fine? Yes, Namita. I hope Namita only asked, right? Yes, Namita. Namita, or who has asked me?
Sir, Manasa, sir.
Manasa. Yeah, is that fine?
Yes, sir.
Yeah. So I just expressed the convolutional integral, that is the bandpass signal of the bandpass system, output of the bandpass system in terms of convolutional integral. Then I'm expressing that in terms of its pre-envelope. Yes, sir. Shall I move up?
Yes, sir.
Yeah. So now let me use the basic property of the pre-envelope. So what is the basic property? Let me say. Okay. The basic property of the pre-envelope is the basic property of pre-envelopes is, so let me write this property. So there is integral from minus infinity to infinity. Okay, so real part of h plus of tau into real part of s plus of tau into d tau will be equal to, okay, will be equal to, say, 1 by 2 times real part of, okay, so integral from minus infinity to infinity, okay, h plus of tau into complex conjugate, okay, complex conjugate of s plus of tau. into d tau Vc. So this is the basic property. Let me a little bit this side. Yeah, I think this is fine, right? So what is the basic property I said? So real part of s plus of tau, the real part of s plus of tau into d tau over the integral from minus infinity can be written as 1 by 2 the real part of h plus of tau into complex conjugate of s plus of tau into d tau. So this is a basic property of the envelope which I am going to use in my above expression. Okay, and before I substitute that into the above equation, so let me just clarify. I think we can take this as a note. Okay, note that I can write s conjugate. Okay, s conjugate of tau will be equal to s of minus tau. Okay, so which is equal to, I can write as s of tau. Okay, so this will remove the complex conjugation in this above equation. So let me call this as equation 6, whatever the property I have written. So let me call this as equation 6. Okay. So now let me apply this property to the equation 5. So if I do that, what can I write? I can write x of t is equal to, right? So substitute wherever this is the real part of s plus of tau into real part of s plus of the t minus tau into d tau can be written like that, right? So I am just substituting this property into the equation 5. So I can write this as 1 by 2 into real part of, okay, real part of integral from minus infinity to infinity, okay, h plus of tau into s plus of t minus tau into d tau. And I said how that complex conjugate will be, that is x conjugate of tau can be written as s of tau. So same way I written this s plus of t minus tau. I think that is understandable, I feel. Yeah. So now let me just substitute the value of h plus of tau and as well as s plus of t minus tau. So we know now how we express the pre-envelope of the signal in terms of the complex envelope. Any one of you can say how do we express the pre-envelope of a given signal in terms of its complex envelope? Yes, what is the expression I wrote? S plus of t is equal to what I wrote? S tied of t into e power j2 pi fc t. Remember that equation?
Yes, sir.
So let me substitute the value of h plus of tau and as well as s plus of t minus tau here. So which is equal to, that is x of t is equal to, I can write 1 by 2 into real part of, okay, so integral from minus into infinity. So for h plus of tau, I can write it as what? H tied of tau, h tied of tau into what? E power j 2 pi fc into tau. Okay. Similarly, for the next term, I can write what? S tied of t minus tau s tide of t minus tau into e power j 2 pi fc of t minus tau. Yes, is this fine? Into d tau. Yes, I'm asking, is this fine? Just have expressed h plus of tau and s plus of t minus tau. That is the what pre-envelope, right? In terms of its complex envelope. So now I think e power j 2 pi fc tau, then e power j 2 pi fc, that is minus e power j 2 pi fc tau will get cancelled now. Here, this term, and here what we have two exponential terms I will get, right? If I expand that, e power j 2 pi fct into e power, that is minus j 2 pi fc tau. I can cancel that. So by doing that, I can write the simplified version of that as 1 by 2 into real part of. So I take that exponential term, whatever is left out, outside only, e power j 2 pi fct, e power j 2 pi fct, okay, and the remaining thing is what? Integral from minus to infinity h tide of tau, right? H tide of tau into what? Yes, what is left out? S tide of t minus tau into d tau. Yes, is this fine?
Yes, sir.
Yeah. Okay, let me call this as equation 7. Hope no, if I move is fine. I hope people have written. Yes, is it copied?
Yes, sir.
Yeah, let me call this as equation 7. So, yeah, now just compare equation 3 and equation 7. So equation 7 is anyhow visible here. I hope if you would have written equation 3 is what? Any one of you can say? What is equation 3?
X of t is equal to
Equation 3.
real part of x tide of t into e power j 2 pi fct.
Very good, right? So that is the output of the bandpass system. So I expressed x of t in terms of its complex envelope. So if I compare equation 3 and 7, so what you can equate? Yes, by comparing equation 3 and 7, what you can write? I'm
X
asking.
side of t is equal to half integral. The whole integral.
Yeah, by comparing equation 3 and 7, right, the complex envelope x side of t of the output signal can be defined in terms of the complex envelope s side of t of the input signal and the complex impulse response s side of t of the bandpass system, right? So let me write that. So this is what? This is x of t, right? Okay. So by comparing equation 3 and 7, okay, so rest of the things you just write in your own words. I can say I can express the what? The complex envelope of the output signal, that is what? X side of t, right? So which is equal to 1 by 2 into integral from minus infinity to infinity into h tide of tau, okay, into s tide of t minus tau into d tau. yeah, S tide of t minus tau into d tau. Okay. Let me put this in box. And let me call this as equation 8. Yeah, any questions to ask so far? Any difficulty at any place of finding it and substituting these things? If no difficulties, I will move further.
Sir, in equation 7,
In equation 7,
we've taken e power j 2 pi fct as common.
not common, man. That is the remaining term. See, e power
Yes,
j
sir,
2
but in
pi
the
fc tau. No, e power j 2 pi fc tau. And here, another term I said, no, e power minus j 2 pi fc tau. It will get cancelled, na?
so, but we have t minus tau in the other term now. So what happens
That
to
is
the
what,
tau?
man. That tau will get cancelled, man.
Okay,
E
got
power
it, sir.
j
Got
2
it.
pi fc tau. And
Yes, sir.
here for minus j 2 pi fc tau will cancel. Only e power j 2 pi fct is remaining. So that I wrote here.
Okay, sir, got
Got
it.
it?
Yes, sir.
Okay. So just now let me put it this in the block diagram form. So that is what we have discussed so far is. So first I took the bandpass signal, right? S of t. Then so this is my bandpass signal. Then I wrote the bandpass system. Right? So this is my bandpass system with the impulse response h of t. So this is my bandpass signal, I said, BP signal. Then I said output of this bandpass system is what? X of t, right? And even this X of t is also a bandpass signal, right? So this is my input signal and this is my output signal. I said X of t is also a bandpass signal. So this is how we describe the input-output of a bandpass system, right? So clear what I said? So now I can describe, right? This is what I can say: input, output, description of bandpass system. Okay. So input, output, description of the bandpass system. How do I describe the same thing in terms of its complex low-pass equivalent model of this bandpass system? Any one of you can guess? Yes? Hope you understood my question. So this diagram, I said this is the description of a bandpass system of input and output relation, right? The same thing, how can I express or describe the complex low-pass equivalent model of the bandpass system? Yes, I know how do I express this bandpass signal in terms of its complex low-pass equivalent. That is what? S tide of t. Hope you're understanding what I'm saying. This S tide of t is a what? Complex envelope of this input signal, right? And this will be given to the what? A bandpass system having a complex impulse response. Okay, complex impulse response. How do you represent that complex impulse response? This complex impulse response is denoted as what? H tide of t, right? I have a system with the complex impulse response H tide of t. So output of this will be what? So I hope I can write now that is 2 times X tide of t with the above equation from equation 8, right? So I can write 2 into X tide of t. So this is my what? This is the complex envelope of the input signal, right? That is S of t, complex envelope of my input signal. And I said it's a complex impulse response, that is H tide of t, and output of that is the what? It is the scaled version. Okay, scaled complex envelope of the output. Envelope of so I am just mapping the above diagram. Okay, above diagram with respect to what? Sorry. So I call this as mapping. Okay, fine. I call this as a mapper. Just I am mapping the bandpass signal into its complex envelope, and the impulse response of the bandpass system has complex impulse response. Then output signal of the bandpass system X of t as its scaled complex envelope of the output signal. Okay. So hope you understood now the mapping of this. What I wrote, this is the first diagram. So this is all about input-output description of bandpass system. And if I can say this is another diagram, which is what? This is the complex low-pass equivalent model. And say it is equivalent model of the bandpass system. The complex low-pass equivalent model of the bandpass system. So from equation 8, okay, from equation 8, I can write that is 2 times X tide of t. Okay, X tide of t will be equal to what? Means I think with respect to the above block diagram, right? That is what the complex low-pass equivalent model of the bandpass system. I can write what? How do I relate here the output of this complex impulse response of a system in terms of its complex envelope input signal? That is what? 2 into X tide of t is equal to H tide of t. Yes, what I can write? Yes, H tide of t is converted with H tide of t. Is this fine? Rather than saying from equation 8, let me say from this diagram. Okay, I can write this 2 into X tide of t can be written as what? the convolution of the complex envelope of the input signal S side of t and the complex impulse response of this bandpass system, right? Yes, is this fine?
Yes, sir.
Yeah. Now, yeah. Shall I move upward? Yes, hope people have copied. Yeah. So now let me try to express this equation in terms of its see, I expressed S tide of t in Cartesian form, right? How I expressed S of S tide of t in terms of in the Cartesian form? Yes, anyone of you can say how did I express S tide of t in terms of Cartesian form? So based on that, I can write the above equation, that is 2 into x tide of t. Yes, Cartesian form. I said no, this and this now I can express in the Cartesian form. What is Cartesian form? That is a plus jb, right? That is si of t plus j into sq of t for this s tide of t, and similarly for h tide of t as what? hi of t plus j into hq of t. Hope I am clear. I can express h tide of t in terms of Cartesian form as what? That is hi of t plus j into hq of t. Yes, everyone agree with this?
Yes.
Yes, I'm not getting. Yeah, is convolved with what? S tide of t can be written as si of t, okay, plus j into sq of t. Okay. So you all know convolution is it a distributive? Yes. Hope you are aware of these rules now. Commutative, distributive. Yes, my dear students, I'm asking people only.
Yes, sir.
Can I say convolution is distributive?
Yes,
Yes,
sir.
no? So, yeah. So because the convolution is a distributive. Yeah. By applying that, how do I simplify above equation? Since it is a distributive, no? Convolution is a distributive. So with that, how can I write the above expression? How can I rewrite? It is 2 into x tide of t will be equal to, what can I write? Distributive property. Yes, any one of you can say. So I can write hi of t is convolved with si of t. Is that fine? First term. Then next term is what? hq of t. Okay, convolved with sq of t. Okay, so this is the first, what I can say, the real part. Then let me move up. Yeah. Yeah, plus j into, I can write hq of t, okay, convolved with Si of t. Okay. Then minus, is it minus or plus? So I'm asking, is it minus or plus? Distributive property. I think you are not applying your mind. So plus, I can write hi of t convert with sq of t. And let me call this as equation number 10. Hope I am with continuity. I think I have given the name for 9. Yeah, you can call this equation as 9. Yes, this one is 9. Yes, hope after applying the distributive property, can I write like this? By segregating real part and imaginary part. You all agree with me?
Yes, sir.
Yeah. Okay. So now let me express that is x side of t. What I said, x side of t that is a complex envelope of the output of a bandpass, that is system, right? In terms of this in phase and quadrature component. So x side of t can be written as what? Xi of t plus j into xq of t. Just I'm expressing in Cartesian form. Okay. So let me call this as equation 11. So by comparing equation 10 and 11, so what you all can say, comparing the real and imaginary part of equation 10 and 11, what can we write for in phase component and what can we write for quadrature component? Hope is it possible to compare and say?
2xi of t is equal to the real part of it. Okay.
Very good, very good. Yeah, then similarly, yeah, others can say, no, yes, Naurin said 2xi of t is equal to real part of the equation 10. That is the hi of t converted with si of t minus hq of t is converted with sq of t. In the same way, I can say 2xq of t is equal to the imaginary part of the equation 10. Okay, so comparing equation 10 and 11, okay, of the real and imaginary part, I can write comparing equation 10 and 11. Okay, comparing equation 10 and 11, the imaginary and real part, I can write as what? So I can write 2 into xi of t, right, which is equal to hi of t is converted with si of t minus hq of t convolved with SQ of t. In the same way, there is the in-phase component, right? This is the in-phase component, and the quadrature component, that is 2 into xq of t, will be written as that is HQ of t convolved with SI of t plus HI of t convolved with SQ of t. So let me call this as equation 12, and this is 13. Okay, so this is the what? First one is the in-phase component, right? So this is the in-phase component, and this one is the what? Quadrature component. Quadrature component. Okay. Yeah. So what you all infer with this? So we came to know what is the expression for in-phase component and quadrature component, xi of t and xq of t. So now looking at this, okay, so I can put this in the form of a diagram also. Okay, that is the low pass equivalent model. So that that will be the end of this, I can say. So is it possible to write? How do I extract 2 xi of t and 2 xq of t from the above two equations? See the low pass equivalent model. What I can say, low pass equivalent model. The low pass equivalent model for what? For evaluating the in-phase and quadrature components of the complex envelope x side of t of the system output. Okay, low pass equivalent model for evaluating the in-phase and quadrature components of what? X side of t. Okay, so x side of t is the what? System output. Yeah. Yes, sir. Hope you're understanding my question. What I'm expecting you people to do it. Just whatever the equation 12 and 3 are there now, I'm asking you people to express in terms of system model, that is in terms of block diagram. Okay, just let me write that. So we have two inputs, right? One is SI of t and another one is the SQ of t. That is the in-phase component of the signal, and another one is what I said, SQ of t. Okay. Yeah. So now from this, okay. So let me put Hope you're understanding what I'm doing. I'm just expressing the above things in terms of the model. Okay. Similarly, another one. Yeah. So now people should tell what to write and in each these 4 boxes. Let me take another input to this. And similarly, let me take yeah. So what do you all expect me to write in these boxes? Just quickly, if you complete as early as possible, then I can leave. If you delay, then it will take time. So can I say this will be my hi of t? Okay, and this will be q of t. Can I say this? And if I do this, so si of t, right, convolved with hi of t, okay, minus, you just see what is the expression for 2 into xi of t. Then xq of t convolved with hq of t. What I get here? 2 into xi of t. Is this fine?
Yes.
Yeah. In the same way, I can write here hq of t. Then this is my hi of t. Yeah. So si of t convolved with hq of t. So what should be the sign here? Both are plus or both are minus?
Plus, sir. Both plus.
Both are
Yeah. Both are plus. Okay, then I will be able to say this is my what 2 into sq of t. Okay. So looking at this model, okay. So this can be implemented without any complex exponential factor, right? Means I will be able to find out the in-phase component and as well as the quadrature component of the bandpass signal, right, without any exponential factor. So this will be simplifying the analysis of the bandpass system. So this is what I wanted to convey. Okay, so this is the time domain procedure for what expressing the complex representation of bandpass signal in terms of its system. Okay, in the same way we can do for frequency domain procedure. So I will take up that in the next class, I feel. Is that fine? Yes, I'm asking, is that fine?
Yes.
Yes, sir.
Yeah. Hope conveyed, got some understanding.
Yes.
Yeah. Go home and again revise once. Okay, definitely you'll be able to understand the importance of representing signal in terms of in-phase and quadrature component. How does it simplifies the analysis of bandpass signal with the bandpass system? Okay, so